The dam did not fail. The mountain did. And everyone knew it could. On the night of October 9th, 1963, a wave taller than a 20-story building erased an entire town in under 4 minutes. The warning signs were not hidden. The data was not missing. The people responsible were watching. This is the full breakdown of 12 reasons it happened and why none of them were accidental. Reason 1. This failure did not begin in 1963. It began millions of years before construction started, inside the mountain itself. The Monte Toc slope above the Vajont Reservoir was not solid rock. It was ancient landslide debris, broken limestone and clay layers tilted directly toward the valley floor. Geologists call this a relict failure mass. The slope had already collapsed once in prehistoric time. It was waiting to move again. SAID, the company building the dam, sent geologists to survey the site between 1956 and 1959. The surface evidence was there, a distinctive chair-shaped depression in the hillside, crescent scars in the terrain. Both are textbook signs of prior slope failure. The surveys missed it or did not report it. The Italian Parliamentary Commission later confirmed the instability was identifiable before a single brick was laid. That undetected flaw became the foundation everything else was built on, literally. Reason 2. Before filling a reservoir against a mountain slope, engineers must know what is inside that slope. At Vajont, they did not find out. No deep boreholes were drilled into Monte Toc before the reservoir was filled. Investigators needed to know the geometry of the failure plane, its depth, angle, and the material sitting along it. That material turned out to be clay seams with a friction angle as low as 5 to 7 degrees. At that angle, the slope could barely hold itself together under normal conditions. The pre-construction investigation relied on surface mapping and shallow tests. SAID's geological advisory team, led by Giorgio Dalpiaz, signed off on the site without subsurface data. The question of what lay beneath the visible terrain was never formally answered. Hendren and Patton, writing for the U.S. Army Corps of Engineers in 1985, confirmed this measurement was never taken before the disaster. Without knowing the failure plane existed, no one could calculate the risk of filling the reservoir above it. Reason 3. Once filling began, the reservoir became an active participant in destabilizing the slope, not a passive body of water beside it. Water rising in the reservoir entered the fractured limestone of the Monte Toc slope and traveled inward. It elevated pore water pressure along the clay seams at the base of the sliding mass. In geotechnical terms, higher pore pressure reduces effective normal stress, which directly reduces the friction holding the slope in place. The reservoir was, in effect, slowly lubricating the failure plane from below. No piezometers, instruments that measure internal water pressure, were installed inside the slope. SAID engineers had no real-time data on what the water was doing beneath the surface as the reservoir rose. Hendren and Patton later back-calculated that full reservoir head pressure was being transmitted directly to the failure surface through the permeable limestone. The slope was weakening with every meter the water rose, and then, in 1960, the mountain sent its first message. Reason 4. On November 4th, 1960, the slope moved. Not catastrophically, but unmistakably. The system had its clearest warning, and it was reclassified as a data point. Approximately 700,000 cubic meters of rock detached from the left slope and entered the reservoir. The impact generated a wave roughly 2 meters high. The slope had demonstrated in real time that it was mobile. This was not a surface crack or a survey anomaly. It was the mountain physically moving into the water. SAID engineers characterized the event as a manageable phenomenon. Reservoir operations continued with adjusted protocols. The company did not suspend filling. It did not commission independent review. It observed, documented, and moved forward. The Venetian Criminal Court later established that the 1960 slide was not an isolated event. It was a structurally identical precursor to the 1963 collapse, on the same slope, along the same failure surface. That assumption, that the slope could be managed, would shape every decision made over the next 3 years. Reason 5. Throughout 1963, the slope was not just moving, it was moving faster, and the data was being collected, read, and filed. SAID operated a geodetic monitoring network on Monte Toc from 1960 onward. Survey benchmarks tracked surface displacement. By mid-1963, displacement rates were measurably increasing. By September of that year, the slope was moving several centimeters per day. In geotechnical analysis, this pattern, called creep acceleration, follows a mathematically predictable path toward catastrophic failure. The CITO method, developed in the same era, formalizes exactly this progression. The monitoring data was held by SAID management, specifically Dam Director Alberico Biadene and Senior Engineer Francesco Sensidoni. The Venetian Appeals Court in 1969 found they either failed to interpret the acceleration correctly or chose not to act on it proportionately. The data was not hidden. It was available. Acceleration of this magnitude, in this context, had one meaning. With the slope accelerating and no evacuation ordered, SAID initiated what it believed would be a corrective intervention. It made things worse. Reason 6. In late September 1963, SAID lowered the reservoir level to reduce pressure on the slope. The physics of what happened next were the opposite of what was intended. This is the rapid drawdown condition. When reservoir water drops quickly, the external water pressure that had been pushing against the slope, partially counteracting its weight, is removed. But inside the slope, pore pressures within the low permeability clay seams cannot drain at the same rate. This is called transient pore pressure lag. The buoyancy holding the rock mass partially in balance disappears. The internal pressure pushing outward does not. The net result? The slope is effectively pushed toward the valley at the moment the intervention was meant to stabilize it. No piezometric data from inside the slope guided the drawdown rate. SAID engineers operated without real-time pressure readings from the failure zone. Hindren and Patton confirmed the permeability contrast between limestone and clay made effective pressure relief impossible within any operationally relevant time frame. The last technical intervention had failed. What remained were regulatory, organizational, and human failures, each one removing a final layer of protection. Reason 7. At every point where an outside body could have stepped in, ordered a halt, or demanded independent review, the legal structure to do so did not exist. In 1963, Italy had no dedicated dam safety inspectorate with enforcement authority. Oversight was distributed between the Ministry of Public Works and regional bodies. None had the technical staffing to evaluate SAID's geotechnical decisions. None held the jurisdictional power to compel operational changes or order downstream evacuation independently of the dam operator. The entire safety framework rested on the operator's own assessments. After the 1960 slide, the event that should have triggered external review, no government body conducted meaningful technical scrutiny of SAID's continued operations at Vajont. Italy enacted its National Dam Registry and formal safety regulations after 1963. The law was written in direct response to what happened at Vajont. Without external oversight, the company that controlled the risk was also the only entity assessing it. Reason 8. SAID did not just operate the dam. It hired the consultants, funded the research, and communicated the findings to regulators. The assessor and the assessed were the same entity. This is a structural conflict of interest. When the organization bearing financial liability for a project also controls the generation and communication of safety data, incentives to minimize disclosed risk are built into the system. Acknowledging unmanageable instability would have required halting a completed, commercially operational dam, a decision with enormous financial and reputational consequences for SAID. Trial proceedings documented multiple instances where SAID's communications to regulators described the slope as under control, while internal data showed progressive deterioration. The Venetian court identified this pattern explicitly in its findings of criminal negligence. Journalist Tina Merlin had reported on slope instability concerns as early as 1959. Sade responded by filing a defamation lawsuit against her. She was acquitted. The risk was not invisible. It was being actively managed as a communications problem rather than an engineering one. Reason 9. Sade did model the consequences of a slope failure. The numbers were wrong by a factor of 5, and no contingency was built for the actual scenario. Internal assessments and consultancy estimates placed potential slide volumes at approximately 50 million cubic meters. On the night of October 9, 1963, approximately 270 million cubic meters entered the reservoir in around 45 seconds. The resulting wave overtopped the dam, which remained structurally intact, by between 70 and 100 meters. No wave run-up model, no emergency plan, and no evacuation protocol addressed an event of this magnitude. Geologist Leopold Mueller had published estimates closer to the actual slide volume, and his findings implied serious downstream consequences. Those warning implications were not converted into protective action by SAID's planning teams. Post-disaster reconstruction of SAID's internal records presented at trial confirmed no downstream inundation scenario for Longarone had ever been operationalized into an emergency response plan. Even if every other failure had been caught, this gap alone ensured the town below had no protection. Reason 10. By late September 1963, the slope was visibly and measurably failing. Casso, the village on the opposite slope, was being partially evacuated due to slide risk. Longarone, directly below the dam, was not. Displacement rates had reached several centimeters per day. Creep acceleration at this rate, in a slope of this geometry, indicates imminent catastrophic failure. The warning window, days to weeks, existed. Longarone sat approximately 1.6 kilometers downstream in the Piave Valley. An evacuation ordered even 48 hours before the event would have saved nearly 2,000 lives. Neither Sade management nor the prefectural civil authorities of Belluno province ordered evacuation of Longarone. The Venetian Appeals Court in 1969 found this failure, given the available data, constituted the legally actionable element of culpable negligence in the deaths of approximately 1,910 people. Alberico Biadene was convicted. The displacement data that should have driven the order was in Sade's possession throughout. With no evacuation ordered, the only remaining protection was an alarm system. There was none. Reason 11. Even setting aside every prior failure, even imagining an alarm was triggered the instant the slope moved, the physics of the wave made survival nearly impossible for Longarone. The slide entered the reservoir at approximately 22:39 on October 9, 1963. The displacement wave reached Longarone in approximately 4 to 5 minutes. The town's population was asleep. There was no siren network, no automated flood warning system, and no pre-established notification protocol for downstream communities. No alarm reached Longarone before the wave. SAID held responsibility for dam-related emergency planning. Italian civil protection authorities held jurisdiction over downstream safety. Parliamentary inquiry documentation confirmed neither had established, tested, or communicated any emergency warning system for the Piave Valley, despite the slope being a known concern for over 3 years. The 4 to 5 minute window was not a surprise. Wave transit time from dam to town is a calculable figure. Reason 12. When the Vajont Dam was completed in 1960, it was the tallest thin-arch dam in the world. It was not just infrastructure, it was a symbol of post-war Italian industrial achievement. SAID operated under government concession in a political economy that had positioned major hydroelectric development as national progress. Projects of this scale carried institutional momentum, the kind that makes it professionally, financially, and politically costly to raise concerns. That pressure does not appear in engineering reports. It shapes which findings get emphasized, which risks get disclosed, and which experts keep their contracts. Tina Merlin reported publicly on slope instability concerns from 1959 onward. She was not an alarmist. She was correct. SAID's response was a defamation prosecution. The institutional climate that produced that response is the same climate in which 3 years of warning signals were absorbed without triggering decisive action. Merlin was acquitted. The disaster occurred 4 years after her first warning was published. This failure did not cause the wave. It caused every decision that allowed the wave to happen. 12 reasons. 1 pattern. At every stage, geological survey, subsurface investigation, reservoir filling, slide response, regulatory oversight, consequence modeling, evacuation planning, the decision that was made prioritized continuity over caution. None of these failures required malice. They required an institutional system in which the cost of stopping was always more visible than the cost of continuing. This pattern does not belong to Italy in 1963. It appears in disaster investigations on every continent, across every decade, in every industry where large organizations assess their own risk. The Vajont Dam is not a historical anomaly. It is a template. 1,910 people died in 4 minutes. The dam is still standing. Disasters are not built in a moment. They are built decision by decision over years, until the system has no margin left. That is the lesson Vajont leaves behind.